Here's pre-calc, it's problem 7-120. It says the amount of water evaporating from a conical container varies directly with the exposed surface area of the water in the cone. The height of the cone is 10 meters. When the height of the water is 5 meters, the radius of the exposed circular region is 3 meters. At this point, water is evaporating at a rate of 0.2 liters per hour. How fast is the water evaporating when the container is full? And then how fast is the water evaporating when it's half full? Well, so they give you this picture. I think I redrew the picture somewhere. So there's a couple things going on here. I think the first thing that might trip you up is you might not remember that varies directly equals, if something says it varies directly, then you're going to say, like, this is y varies directly as x. That's a direct variation equation. So when you first encounter this problem, you want to think about how the water varies directly with the surface area. And we're going to let W equal the rate of the water evaporation. And so if you this was kind of a hairy problem. If you kind of sift through, I'm going to actually get this picture. This is a nicer picture right here. If you sift through all the words, basically you're going to want to find out how fast is the water evaporating when the container is full. And we know that there's a direct variation problem because it says it varies directly. And direct variation, like I said, is y equals k times x. So what we need to find out is k. So here's how I found k. I said the water varies directly as the surface area. And then they told me that when the surface area was, they said when the height of the water is 5, the radius is 3. And at that same point, it's evaporating, the rate it's evaporating is 0.2. So just these numbers here, I plugged in the 0.2 because that's the rate of the water evaporation. And then surface area, they told me when the height of the water's 5, the circle it makes, this little circle, has a radius of 3. And so that's where this is all coming from right here. And I want to find out what k is. So I just divided both sides by 9 pi. And then I found out what k is. So then now I know that here. I know that k is 0.2 over 9 pi. Okay. Surface area is pi r squared. So then I went and I wanted to find out what was in letter A. So letter A says, how fast is the water evaporating when the container is full? So when the container is full, I can figure out what the radius is when the container is full because I have similar triangles here. This little triangle, when the height is 5, the radius is 3. But these are similar triangles. They have this right angle and they share this angle. So when the height is 10, the radius is 6. Okay, so that's where I'm getting this 6 from. And then, what did I do here? And then they want to know how fast the water is, like, because we know that W equals K times surface area. They want to know how fast is the water evaporating when the radius is 6, because they're asking about when the container is full, and we know that's when the radius is 6. So I just get out my formula. I already know what K is, because we did this work over here. So I plugged K in here. And then the surface area, when the radius is 6, that 36, that was 6 squared. I already did a little work here. Right, pi r. The surface area is pi r squared. And then I went ahead and just did this like cancellation, like the pi and the pi went away, and the 9 goes into 36 4 times. And then I went 0.2 times 4 is 0.8. So that's how fast the water is evaporating when the container is full. Because that's when the container is full, it has that radius of 6. So then it asks, well, what about when the container is half full? So I know, and then they gave us a little clue. They said, remember that the volume is 1/3 times pi r squared, 1/3 pi r squared h. So I took the volume. Volume is 1/3 pi r squared h. But I solved for 60 probably on another piece of paper. Or I said half, I wanted it half full. Where did I do my work to show? Here. Here's the work I did to find out how much it holds when it's full. So 1/3 pi r squared h. That is when this thing is full. And I want to find the volume when it's full, so all I had to do is like 6 squared is 36 times 10, that's 360. 1/3 of 360 is 120 times pi. So 120 is the full container. But they're asking me about when it's half full. So when it's half full, I know it's half of 120, so that's where this 60 comes from. And then, so then I will go ahead and, I think I did the work right here. So what's R? Because I still want to use this formula, like, because I already know K, so I can plug K in right there. And if I just had the darn surface area for the half full cone, then I could solve for W. But I can't have the surface area if I don't know what R is. So I'm doing this whole thing just to find out what R is. So what is R when my container's half full? So I get the volume formula, and then I plug in 60 for volume, and then H. This was interesting. H, I had to get help from the answer book for this. We don't know what H is, but we can find out what H is in terms of R. So, and here's how that happens. This right here, this 5, that's H. And this is R, 3. And they gave that to us. And they also said that the whole height is 10. And when the whole height is 10, then R is 6. So I have two similar triangles. So what I did is I said 3 is to 5 as R is to H. And then I can do cross products. Actually, I did them. I'll show you where I did them. I did them right here. Or I said 5 is to 3 as H is to R. And then I did cross products. So 3 times H is 5 times R. And then that gives me H. And H gets plugged in here. So now I have everything all in terms of R. So that was a nice little trick that I won't take credit for. And then I just did my algebra to find out what R was. So I like crossed out the pi's. I think I just multiplied these two together and got the 5/9 R cubed. And then I multiplied by the reciprocal of 5/9 on both sides and solved it. And I got 108 was R cubed. So R was the cube root of 108. But that's just about 4.76. But now I have that. And I can plug it into my direct variation formula from the very beginning, it said that the rate of the water evaporation varies directly with the surface area. Well, now I can find out what my surface area is, because my surface area is pi r squared. So, and we already had K, because we found that out in the very beginning. So K was 0.2 over 9 pi times pi r squared, that's surface area. So this is a little ugly, but I just stuck it in my calculator. I crossed out the pi's, and then I went 0.2 times the cube root of 108 squared divided by 9, and you get this. Sorry that was so long, but it's kind of a complicated problem. Was that the end, or is there more? That's it.